Yes, hi, my name is Andreas Spanias, and I'm a professor in electrical engineering at Arizona State University. I'm also a center director for the SenSIP Signal Information Processing Center, which is also an industry university cooperative research center. Let me see quickly if I can share my screen. Um, and Okay, so the title of my talk today is going to be SenSIP Center Research on Machine Learning for Solar Systems. And this is based on research projects that the center hosted and is currently hosting as well. There is the NSF award with the IUCRC, the Cyber Physical Systems project, and the IRES project that they are related with this. And more recently, we got an MRI award actually this last August. So the topics today are on the research activities of the Industry University Center. I will give you an introduction of what is an IUCRC and how it operates, the use of machine learning in monitoring and optimizing solar arrays, the NSF Cyber Physical Systems program and some of the results. And then I will also describe workforce development programs that we have on sensors and machine learning for solar energy systems. We are hosting 3 workforce development programs, and we are partners in another 2. Specifically, I would talk about the IRES program. IRES stands for International Research Experiences for Students, and this is specific to solar energy and machine learning, and it's a partnership with the University of Cyprus KIOS Center of Excellence. A little bit about the center first. The center is based on industry membership. We started back in 2007 as a Board of Regents center, and then this evolved into an industry consortium. We recruited our first members that included back then Raytheon, Intel, and National Instruments, and then we applied to the National Science Foundation to become an official industry university cooperative research center. With that designation, actually, we get funding from the NSF. We also have obligations. We have to maintain at least 5 industry members that they're paying membership fees to the center. Through those membership fees, basically, we issue students that they're defined and approved by the industry advisory board. So we have topics that they get defined by the IAB, and then we run sessions where faculty will propose projects, and then the IAB would review them and approve them or disapprove them. And we always run a series of projects. Typically, we will be running every given year 5 to 7 industry projects that they are monitored also closely with the member of the IAB. And then their results are presented twice a year in IUCRC meetings, typically held in partnership with a University of Texas at Dallas and also the University of North Texas. We are in a partnership relationship, and they have their own members there as well. We hold meetings twice a year, and they bring their industry members as well. Together, all these 3 centers, they have more than 20 industry members. Just to give you an idea of the programs at ASU, we've had programs with Intel on architecture design and also on autonomous vehicles more recently. Surveillance systems and array processing and radar by Raytheon. NXP works with us on sensors and sensor calibration and sensors for fault detection. We work with Lockheed for radar. We work with LG on internetworking. We Sprint on sensor localization and mobile device localization. Now Sprint has become part of T-Mobile. And Qualcomm on computational cameras and object tracking. onsemi signed with us last year and is working on machine learning for electronics. And then we have several SBIR-sized companies that you see them here on the bottom, and they're working on smaller projects. So the program at hand here is, can we use machine learning to detect and classify photovoltaic faults? So the idea here is the following. We started some of this engagement in this area back in 2011 when we started working with a Japanese company, a subsidiary of Mitsui. And at the time with the Fukushima accident, they were trying to deploy massive solar arrays in that area, and one of the problems they face is to really continuously monitor them, and if they can also control them from remote because of the radioactive issues that they have. And they awarded a contract at the time to our center to do some studies on data and see if we can work with them actually to develop hardware and algorithms to monitor and remedy faults that we may be able to find using different algorithms from remote. So this project later evolved to a project funded by NSF back in 2014. We got a 3-year project from NSF. And then in 2016, we got a cyber physical systems program from NSF that was more comprehensive with 5 faculty participating. That one included also using vision theory and machine learning to predict shading. Cloud shading is a problem for solar arrays. Of course, it will reduce the power output, and soiling and associated problems as well. Can we use machine learning to optimize topology, connection, and maximize power? We have shown back then that if you have partial shading, if you reconnect the solar panels in different configurations, you can actually increase the output under shading conditions. And then other problems is, can we manage transients in power electronics associated with solar arrays and inverters in particular? And can we also work on communications related problems? This shows you a slide. Actually, this slide is the one that we used in the CPS PI meeting last November 2019. We've had a presentation there by all the PIs for different projects, but this particular project, we showed them work on fault detection and on solar topology optimization. And we had basically one of the results that I'm going to come back to is that we've been able to show that we can raise the output under shading by as much as 16%. Some of this work was patented as well by our center. The overview of the system that we're working on for solar monitoring and control is shown here in this diagram, where you can see the solar panels, the irradiance sensors that they're sensing irradiance, and then the smart monitoring devices, as we call them, they contain a radio, a microprocessor, relays, and they communicate with the world. So at any point in time, you can actually see what each single panel in a massive solar array is producing. And also you have the ability to disconnect it, you have the ability to bypass it, you have the ability to reconnect it in different configurations. And we have lots of signal processing and machine learning work involved here, as well as imaging and video to predict shading. And some network related research is in here. You see the different areas here that they are involved in this project, and it's engaging, as I said, it's engaging actually 5 faculty and 5 PhD students right now. And we also have the 2 undergraduate students that they've been funded from this as part of a program that is called Research Experiences for Undergraduates. And I will describe later on also the IRES, but you see areas here: fault detection, shading prediction, and topology reconfiguration. And then data analytics is part of this. Just to describe to you a little bit, fault detection, we get measurements of voltage and current, and typically these measurements, if you observe them, they fall on a curve such as this one here. And what we have here in this red cluster, it's really the area where we get maximum power. And if we start seeing data clustering away from here, then this becomes suspects for a fault on that particular panel. And then you have the ability, for example, if the panel became an open circuit, it's taking out the whole string of series panels, and you can actually bypass it. So using this hardware, this intelligent hardware that will detect the faults, and then at the same time, you can issue instructions automatically to bypass, or as I said before, reconnect it. So we started with simple statistical analysis in the beginning, but gradually we went into using machine learning. And the most recent thing we've been doing here is to train a neural net using voltage and current data to recognize different faults, so you can detect, localize, and classify at the same time. And we have a customized neural net now, a prune neural net that we developed using statistical methods that is customized to this problem. And we actually filed a patent of this as well. So the second part of the project, as I said, is shading prediction. And when we detect shading, we can actually instruct this smart monitoring device to switch around the connection topology. And we can choose among four different topology, the series parallel, bridge link, and the honeycomb, and so on. Those are established topology connections for solar panels. And we've shown actually by using a neural net, after we train it, we can up the power by 16%, which is significant, okay? A maximum of 16%. So this is a result that motivated this research, and we show here that by connecting changing the array topology, you can actually increase the power. And more recently, as I said, we got the power increase as much as 16%, which is considerable. This shows you our experimental facility at the ASU Research Park. And we have built here, with some support both from ASU and from sponsors, we built this facility with 104 panels. And you see here, what I'm showing you here are the smart monitoring devices that they have the sensors, the actuators, the microcontroller, and the radio that enables them to communicate with the internet. So through secure internet, then you can monitor what each and every panel is producing here. And at the same time, you can change the type of connections. The default connection is, we have 8 series strings that consist of 13 panels each, but you can change them into different topologies based on instructions that we obtain from shading data and from the neural net that is continuously optimizing this. So basically, this is what we call the smart monitoring device. You've seen it before. This is what is mounted underneath each panel. The idea is in the future to miniaturize this and possibly then try and integrate them. But this one has a microcontroller, it has relays on the bottom, and it has a radio, and it has cables that it interconnects to the neighboring solar panels. And then by using this device, actually this becomes a network now, and every single panel has an IP address. And you can it really renders this as an IoT energy system now, that you can address from remote, you can obtain energy, and you can reconnect in different ways. The cyber physical systems outcomes, I mean, we've had detection accuracy using neural nets, which is above 90%, and we were very happy with that. And we submitted a patent. We have a provisional patent, and a full patent is pending. We have output power increases from 10 to 16% using, again, shading prediction data, and also using a neural net to test the different topologies and determine the optimum topologies. And we published papers. In fact, we recently published a book in August 2020. This is a new grant that we have. It's called Major Research Instrumentation. We obtained this in August 2020. This is the book that we produced, and it has both the investigators and the students involved. The new grant involves 6 faculty working in signal processing, machine learning, communications, and inverter technology, power electronics. And we look forward actually to working on this to produce the next generation smart monitoring devices. Now I'm going to talk to you a little bit about this international research experience programs that we have with the University of Cyprus. We applied back in 2019 on this program to use and train machine learning, train students in machine learning for energy systems. The idea is that we get faculty advising both from the SenSIP Center and from the University of Cyprus KIOS Center. And the idea also was that we have a bit of complementary expertise with the two, but in this area, we did work out a lot of the research here with utility scale solar arrays. They've had more experience with rooftop systems there. So the idea of this collaboration is to see if we can transition some of what we learn from our cyber physical systems research to rooftop installations. So students were recruited and they were embedded in this research, and they actually traveled to the University of Cyprus and stayed there for 4 weeks working with the professors there that they are partners in this IRES program. So the idea of the IRES, the objectives, is to immerse students in international machine learning research, embed the students in the KIOS Center at the University of Cyprus, provide them not only knowledge on the technology and enable them to do research, but also give them a little bit of knowledge in terms of standards and policies. Ideally, the project was to have 6 weeks experience in Cyprus. We actually in 2019 we could only do 4 weeks because of logistic difference that we had, but we did a lot of communications all through teleconferencing in the summer of 2019. And the idea is to enable the students to innovate in this area and also provide also cultural experiences. In fact, that was a required section in the proposal to ensure that we get also the students exposed to the culture there. You see here the students traveled to Cyprus back in 2019. They were embedded in the power systems lab. They had training sessions, and they were actually working on research in different areas, and they were advised both by senior PhD students and faculty there. A picture here on arrival to the KIOS Center back in June of 2019, 4 students and myself and the faculty advisor there and copy of the project, Dr. Kyriakidis. Unfortunately, we lost Dr. Kyriakidis last year, but he contributed quite a bit on the project. We have 2 of his research professors now that they're helping us with this. And we work with KIOS centers because KIOS is probably the largest research center at the University of Cyprus with several faculty. They have a major EU teaming project with Imperial College in London. They have a joint degree with Imperial College. And they recently, actually, I learned that they got a major teaming ERC as well, which is a major grant. So they have several tens of millions of dollars of research going on there. But for us, even more importantly, is that they had experience in power systems and solar energy. So we did take the students there and we embedded them in the labs, and they work with the faculty there. We had a schedule for the students as part of this workforce program to get trained in machine learning at ASU first. We held a boot camp, and actually we put them together with the RAU group that we're running at SenSIP for 3 weeks of intensive pre-training. A couple of the students actually were involved as early as January in this research. So by the time they went to Cyprus to spend time there, they had very decent knowledge of machine learning algorithms, and they had data to work with and so on. And then the program also involves a post experience. So this is the schedule. As I said, instead of taking 6 students, we ended up taking 4, and we stayed only for 4 weeks there, but they ran the rest of their research at the ASU later on. This is a picture from a visit at the time to the university rector there. So the 4 students and the 2 faculty PIs and the rector, who is the equivalent of a president that we have here in the United States. The students produce research reports. 2 of the students produced papers actually that they presented. There was an assessment of the program by CREST, an ASU entity that assesses different types of research and education programs, and the results actually were quite good in terms of gaining knowledge in machine learning and the student satisfaction from travel and so on. As I said before, part of the experience was to get a little bit of knowledge in terms of cultural experiences, so that we encourage the students to visit historical sites during the weekend, and they did that. And we had also the students present there at the conference, a small conference that is held every year, where graduate students present their research. And actually that was a good part of the experience, to get them to present to an international audience. This year, because of COVID, we couldn't get the students to travel there. We ran a smaller program after permission from the program manager, only with 2 students, 1 undergraduate and 1 graduate, and everything was run through Zoom meetings. We had at least twice a week meetings, and actually the students actually talked to the faculty in Cyprus even more often than we as the faculty PIs did. And actually we had pretty good results with this, and which we will be reporting very soon. This year, the students use unsupervised learning algorithms to implement soiling detection on panels. And we were very lucky that we had one of the research professors there also was involved with a company that was able to give us lots of data. And they were able even to give us some ground truth data as well. An innovation in positive and labeled learning by our PhD student will be published soon, and a patent pre-disclosure was submitted. And the IRES session this year actually is still ongoing this fall. One of the ideas there was, again, to do some research on the soiling of different rooftop installations in this case, and the students worked quite hard actually to identify from remote where the solar sites are, and what sort of output they were obtaining from the sites. And you see here the island of Cyprus is in the Eastern Mediterranean, a small island, but it's quite, the climate is very similar to Arizona in many ways, and it's a dry climate, and it's kind of ideal for solar installations, and there's a lot of that going on now. I should also tell you that we engaged 2 teachers here from local high schools in Arizona, and actually these teachers work very hard, and they had good outcomes actually from their research that we hope to publish as well. Something more general now about the center. We do have international relationships and MOU signed with 5 different universities, and actually 3 of these universities we got the jointly funded programs, and then we look forward actually to building our network of international collaborations. That's one of the missions of the center. Patents, it's an activity that is the center has, and between we established 11 patents. Maybe if you also look at the patents of our affiliated members, we probably have more than 20. There's several provisional patents also that have been established. We did produce research monograph booklets that in most libraries actually you can obtain them for free if the library has a membership with Morgan and Claypool. So in conclusion, we did do research in solar array optimization as part of the cyber physical systems program, and we've had significant outcomes. The most significant, elevating power up by as much as 16%. under shading conditions by reconnection of the network. Based on this, we developed also this workforce development program that was international, and we collaborated with the University of Cyprus. We trained between 2019 and 2026 students. We also trained 2 teachers to work in this area. There are several other industry projects. I showed you those in the beginning in several machine learning and sensor applications, including health and security. Many of our members work in these areas. So some of this slide here shows you some of our research and training products, which I've already described actually briefly. We have 3 workforce programs, and we're partnered in another 2. There are several active research projects with NSF and other agencies. We have an LT dedicated facility at ASU. We have synergies with other programs. We have a graduate certificate for training of students, and we have the same MOUs with international institutions, and you can find a lot of those on our website. Some references here associated with the solar research specifically, including the most recent one is this book we produced with the co-investigators on the CPS project and all the students. And with this, I'm going to go ahead and close now. This is a recording, so I won't get to answer live your questions, but please feel free to send me email if you have questions, and visit our website. You'll SenSIP.asu.edu. You'll find a lot of this information and specifics on the projects. And I want to thank you very much for attending the presentation, and I'm hoping to hear from you.